Hello, my name is Christopher Hamkins, and I'll be introducing the paper Solutions in Minimal Conflict Search for Product Configuration, written together with Sebastian Velten. The work is a case study and was motivated by an urgent real-world need for assistance in product configuration system. The product models had become so complex that even their designers didn't always understand all the implications of a given constraint. The users had difficulty finding valid solutions, and when their requirements were in conflict with the model, it was practically impossible to resolve the conflict manually. Modelers often spent days trying to determine the source of conflicts in their models. This was the motivation to start the work. The product configuration system would not have been a success without it. A central concept in the work is that of the minimal conflict, a set of constraints that cannot all be enforced simultaneously. It is a conflict, but such that removing any one of the constraints would resolve the conflict. A given overall set of constraints can have many minimal conflict sets, and to find an overall resolution of the conflict, you need to resolve every one of them. The resolution requires relaxing at least one constraint from each minimal conflict. We therefore developed an algorithm to find all the minimal conflicts in a given problem, which we call the minimal conflict bottom-up binary search, or MinCBBS. It works by alternating between finding unexplored candidate sets, namely sets of constraints whose feasibility cannot be inferred from those sets already checked. When it finds a conflict, it reduces it to a minimal conflict using a binary search. The steps are repeated until there is no more unexplored set to check. The BBS algorithm to find a minimal conflict in a set of constraints known to be a conflict works by dividing the field until it can find or determine that an element is in the minimal conflict. The field is increased or reduced again to find candidates for the next attempt depending on the feasibility of the last attempt until a proven minimal conflict is discovered. The algorithm would basically alternate between expanding and reducing depending on the conflicts discovered until it has one minimal conflict in the original set. The overall algorithm, which we demonstrate on this slide with the model presented in Lifferton's paper, starts by working on the complete conflict set, then proposes additional candidates by removing constraints from the minimal conflicts found so far from the overall set and checks their feasibility. When a conflict is found, it's reduced to a minimal conflict. The cycle continues until there are no more unexplored conflicts. The performance of the algorithm is much better than those previously used in the project and perfectly acceptable for providing resolutions to the end users in real time during interactive use of the product configurator. It has the desirable property of starting to report minimal conflicts immediately and continuing to produce them at a relatively steady rate until all are found. Each line in this diagram represents one test case, and one can see that the number of minimal conflicts discovered rises roughly linearly with running time. So that was a very quick overview, but this was not an ivory tower exercise. It was motivated by a very practical need for assistance for the users. During the work, each new improvement to the method was put directly into use in the productive system. Our end users and product modelers were enthusiastic about the support it provided. In the paper, we also give some more results for model pre-processing to improve performance and more information about the exact type of constraints used in the product models. We hope you found the presentation to be interesting and made you curious about the paper itself. Thank you very much.